So now we continue our discussion about primary decomposition. First, a proposition which gives some light on primary ideals. So let R be Euclidean P a prime ideal and M a finitely generated R module. Okay. And we want to understand what it means for M to be P primary. Okay. Then the following are equivalent. 1. 0 is a primary submodule of M, and P is the radical of the annihilator of M. 2. So this is sorry, I misspoke. We are not saying what M is P primary. We are trying to understand the condition when is 0 a primary submodule. Okay. This is the same thing as what we were discussing in the previous lecture. We were discussing N is a primary submodule of M. That is really a condition about M mod 0 inside M mod N. So we are just restricting ourselves to the 0 submodule. Second condition, P is a minimal prime. Okay, I will define this immediately after I state this. Minimal prime of M, and every element of R but not in P is a non-zero divisor on M. And 3, there exists some T such that P to the T annihilates M, and every element of R but not in P is a non-zero divisor on M. Okay. So sorry, I missed 2 definitions here, which I should have done before I got to this. So let's just backtrack and define those things. Definition. Support of M is a set of prime ideals P such that M localized at P is not 0. Okay. In particular, the annihilator of M must be inside P. Okay. We have not inverted anything. We have inverted elements outside P, and in this case we have not inverted anything that annihilates M. Annihilates all of the module. Okay. So this is what support of M is. Okay. And min M is the minimal elements of support of M. So this agrees with the definition of min of a ring that we used in earlier lectures, which is just to say support of a ring is all of spec R. So min is minimum elements of that. Okay. So this is just the definition, and here is an exercise. R Euclidean, M finitely generated, then support of M is V of the annihilator of M. Annihilator of M is the elements of R that kill all elements of M, and okay, so this is what this is an exercise which you should do, and okay, So this is what support is, and so therefore, in conclusion from this is min m is minimal elements. I mean, in this context, R Noetherian m finitely generated. This is same thing as min elements of R mod the annihilator of M. Okay. Support of M is V of this, and its minimal elements are precisely the minimal elements of the spec of this ring. Okay. So this is really spec of. We often abuse notation like this. Technically, this is a subset of spec R. This is some other set which maps into this as a closed subset, but we will often not worry about these differences unless there is something to be done in the world. Okay? So this is one. And another definition was of non-zero divisor. R in R is a non-zero divisor if there does not exist X in M, non-zero divisor on M. Sorry, I'm defining this term. If such that Rx is 0, or equivalently, the map M to M given by multiplication by R, okay, which is some X goes to R times X, the R linear map, is injective. Okay, so this is what will be a non-zero divisor. Now let's go revisit the proposition which we need to prove. Okay, so we are in an Noetherian ring, finitely generated module, and we ask the question, when is 0 a primary submodule with this property? And then, so 1 implies 2. This is proof of the proposition. Okay. 1 implies 2. Let R be R but not in P be. If R is a non-zero divisor, I'm sorry, if R is a zero divisor, then there will exist a Q which is strictly bigger than P, okay, and Q will be associated to M, okay, and this is a contradiction. The point is that where was it? Yeah, if P is the radical of the annihilator of M, then every element inside M will be killed by some power of P, and hence among the ideals that are killed, among the associated primes, P will be there, but because 0 is primary, among the associated primes of M, P will be there, and because P is primary, I should just write. Okay, sorry, I'm saying too many things. Okay, so note, since P is the radical of the annihilator of M, okay, for every X in M, the annihilator of X contains a power of P. Okay. And for every x contains a power of p, which now implies that p is associated to M. Okay. However, since 0 is q, since 0 is p primary, 0 is primary, okay, associated primes of M is a singleton set, okay, but p is already there, and that is the contradiction here. You cannot have a q different from I, which is q different from p, which is associated to M. Okay. Now 2 implies 3. Okay. So let's look at 2. So part of 2 and 3 are the same, which is about some things being non-zero divisors. So 2 says p is a minimal prime and every element of R mod p is a non-zero divisor. Okay. From this we have to conclude this part, and the rest is just the same. Okay. So let's do that. Not from all of 2 we will assume that p to the t kills M, okay, and then the rest is just rewriting. Okay. Let Q be a minimal prime of M. Okay. Yeah. So P is a minimal prime of M, and every element of R but not in P is a non-zero divisor on M, which means that one cannot have associated primes outside of P, meaning every element outside this is a non-zero divisor. And remember that associated primes are maximal, associated primes contain zero divisors, because P has, if Q is an associated prime, Q must kill something inside something inside M. Okay, so if Q is a minimal prime, so I will have to use the fact that minimal primes are associated, which I will prove in a little while. Okay, so this will be proved in a little while, shortly. Okay, but we just observed that every element outside Q, outside P, is a non-zero divisor. So therefore, a prime ideal not other than prime ideal not contained in P cannot be an associated prime, since every element in R mod P is a non-zero divisor. Every associated prime is a subset of P. Okay. In other words, Q is a subset of P, but both are in min R. Which means that Q is equal to P. Okay, so that's what we have. So what does it say? This. Okay. So now this one says that. So this one says that min of M is a singleton set P. So from these two statements together, that P is a minimal prime and every element outside P is a non-zero divisor, what we concluded is that P is the minimal primes over M is a singleton set containing just P. Okay, so which now implies that the radical of the annihilator of M, okay, remember we proved a while ago that radical of an ideal is the intersection of prime ideals containing it, and this is the support of, the prime ideals containing this is precisely the support of M. The minimal elements of those are precisely P. So therefore, when you intersect, you just have to intersect the minimal primes, and this is equal to P. Okay. And now we can observe the following. Since M is finitely generated, sorry, we don't, we've already used, okay. Since R is Noetherian, J, radical of J to the T is inside J for every ideal J. Okay. What one needs is that this ideal is finitely generated. Remember, this is the radical. So if this is finitely generated by, let's say, x1 through xn, then x1 to some t1 is inside J, x2 to some t2 is inside J, and then we can just take some very large power, and then arbitrary linear combination of the x's will also be inside J, and all that is used here is that this ideal is finitely generated. Okay. So R is Noetherian, therefore for every ideal J, this is true. Okay. Okay. So this proves this proof gets 3 from 2. Three implies 1. Okay, so 3 says that some power of P annihilates M. Power of P annihilates M, and every element of this is a non-zero divisor on M. Okay. So since P to the T annihilates M for some T, the radical of the annihilator of M is P. Okay. In other words, the minimal of M is the singleton set P. Okay. And sorry, I still would have to use the fact that this is there are no other associated primes. Okay, so now we need to show that, okay, so since every element of R mod P is a non-zero divisor, okay, for every associated prime, Q must be a subset of P. Because we discussed this a little earlier, because if Q is an associated prime, Q has to kill a non-zero element of M, which means that elements of Q are themselves zero divisors on M. Therefore, it cannot belong to this set. But P is a minimal prime, so that, which means that associated primes of M is also this one. Okay, but what does that say? This now says that 0 is P primary in M, and the radical of the annihilator of M is P. Okay, so this proves the proposition. Okay, so one can think of it in the following way: if so what does it say? I mean, what do elements inside R look like on M? So elements that are outside, so in this situation, so remark, okay, so this is what a primary submodule, this is what a primary submodule of a module means. So R Noetherian, I mean, sorry, not that this is what it means, but it has the following property: M finitely generated and N inside M submodule. P is a prime ideal. So So I'm just rewriting the previous proposition in a slightly more convenient or familiar way. Then if assume that n is p primary as a submodule of M. So n is a p primary submodule of M. Okay. Then every element of R, okay, let's write it into, okay, let R be inside R. So R can act only in two different ways on M mod n. On okay, R, if R is not in P, then the map M mod n to M mod n is injective. Okay, and if R is in P, then the map is nilpotent. In other words, if you compose that map enough times, it becomes a zero map. Okay? So that is composing it. With itself. Multiple times will give the zero. Okay, so this is informally one can think, I mean not very informally, but we just proved it, that elements of R act either as non-zero divisors or as nilpotent elements. This is a special property about primary submodules that an arbitrary submodule will not have. Some examples and these irreducible and primary components. So in this proof, we use the following, that minimal primes are associated. So that requires a proof, and we will prove now. But before we prove that, we need to make an observation about associated primes and localization. Associated primes and localization. Okay. So this is a situation. R is a ring. U is a multiplicatively closed set. Okay. And M is an R module. Suppose that P is associated to, then what does this say? This says that there is an R linear map, injective map from R mod P to M. So this implies this. This is R linear. Okay. Now, we could have just localized this whole map. This gives a map from U inverse of R over P, injects, okay, localizing preserves injectivity to M inverse U. What is this? This is isomorphic to U inverse R mod P, U inverse R mod P extended to that U inverse R. Okay. So this is R, U inverse R linear. Okay. So in other words, so we should assume in this situation U does not intersect P. Okay. So that P extended to this is something non-trivial. So this is not the zero ring. So this now implies that the extended ring is associated to U inverse n. Okay, so this is what Okay, so an associated prime remains an associated prime after localizing, provided the prime itself didn't become the whole ring. Okay, so we inverted something in the complement of that prime. Okay. So this is one statement. So now suppose that R is Noetherian, in addition to the previous things, and assume that suppose that U inverse P extended to U inverse R is associated to U inverse M. Okay. So therefore, there is an injective map from R linear injective map from U inverse R to P U inverse R to U inverse M. Now, the fact that I is finitely generated in this context gives us the following, which is that homomorphisms from over U inverse R from U inverse R mod P U inverse R to U inverse M is exactly the localizations of the maps, R linear maps from R mod P to M. Okay. And this will give an injective R linear map from R mod P to M. Okay. And this now implies that P is associated to M. Okay. So this is, okay. So therefore, the conclusion is that if R is, so conclusion that if R is Noetherian, U multiplicatively closed, P intersect U empty, okay, then P is associated to M if and only if P extended to the localization is associated to just minor confusion. This is associated to M, and here we are talking about R modules, and here we are talking about U inverse R modules. Okay. If and only if this one. In particular, okay, P is associated to M if and only if P RP is associated to M localized at P. Okay. So this is what we would want to use. Okay. So now let's prove the following proposition, which was what we had used in the previous proposition. Okay. The minimal, so R Noetherian, M finitely generated, then the minimal primes of M are inside the associated primes of M, and all of these are actually subsets of support of M. Okay. So why? So let's prove these things. So minimal inside support is by definition, these are the minimal elements of that. What we want to show is that minimal primes are associated to the maximum to M. Okay. So let P be a minimal prime. Okay. Then we have R. Then over the over the local ring, R localized at P, its maximal ideal PRP, support of M localized at P over this ring, okay, is just PRP, because after we localize, the only primes that would remain are primes that are inside P, but M is not supported at any prime which is inside P other than P itself. Okay. So this is what it is. And okay, so first observe that associated primes of M, okay, so P associated to M implies that P is associated to M mod PRP is associated to RP, MP. So M localized at P is not 0. Okay. So in other words, okay, so if support is all of this and the associated prime is non-zero, is non-empty, then it can only be one value, which is this, okay, which means that associated primes of M localized at P, okay, as an R localized at P module is PRP. This is where minimality is used of this one, okay, to conclude this and then use this fact to do this. And this now implies that P is associated to M. That was what one can use localization both ways because it's an Euclidean. Okay. So now so this proves that minimal primes are associated, and we just observed in the proof of the previous step itself, but let me just clarify this. If P is associated to M, implies that P is in the support of M. Okay. In other words, P does not kill every element inside M. Okay. So that is because M localized at P, P is associated to M localized at P. Okay. And therefore M localized at P is non-zero. Okay. So this is M localized at P is non-zero, and then we have this. Okay. So this is the end of this lecture, and in the next lecture onwards, we will continue with exploring further properties of these primary decomposition.